So we were almost at the end of my knowing when to stop marathon. So the final thing I want to discuss is this conjecture of Polya having to do with the uh, uh, accumulated Liouville function. So let me just remind you what it is and show you what it looks like in Maple. So the idea is that you run through all the integers, and then you say, suppose I have a fixed integer like 100. Now I compute the value lambda of I for all i's between 1 and 100, and I add all these numbers up. What is lambda? Lambda is minus 1 if we have an odd number of factors in an integer, and it's plus 1 if we have an even number of factors um, in the prime factorization counted with multiplicity. There's something called big omega built into Maple that computes the number of factors, prime factors, and then so I'm just making my little program here return minus 1 to that power. You can see that I put in an option remember, and that is in order to save myself some work. Of course, when I'm computing lambda, when I'm doing a graph like this, right, I'm computing lambda of 100 and lambda of 99 and of 98 and so on. And those numbers are, sums of more or less the same sequence of ones and minus ones. So I'm putting in option remember not to make a recursive call, but simply to make sure that once this number has been computed, once it's stored, so I don't have to do it again. That's not super efficient. I could do much better, but it's very easy to code. And you can see when I'm doing this way, the first thing we notice is that all the values that we see are not positive. They come up and get exactly to be 0 up here and in the beginning a little bit. We can go further to say 1,000 with no big sort of problems, but already at 10,000, this is going to take a little while because essentially Maple has to compute the prime factorization of all the numbers to up to 10,000 and then add up some pluses or minus ones relative to that. So let's wait for it. So this is what it looks like, and you can see it sort of seems to move a little bit away from the x-axis. So this is the basis of Polya's conjecture that this remains non-positive for all values. And it turns out that this is false. Actually, the way it was disproved is quite interesting, so I want to spend more time on the history of this than how you would actually do it in Maple. It's more or less described in the book how you would do it in Maple, but it's quite computationally demanding and takes several hours. So let me just give you the main idea. And before I start explaining the main idea, let me start this thing here in Maple because it's going to take a little while for it uh, to complete. So what I want to do is I want to show you this impressive inequality established by Ingham. And actually, this is some uh, theoretical explanation that was done not so long after Polya's conjecture. So what happened was that when this was established, so Ingham essentially proved that if Polya's conjecture would have been true, or was true, then lots of very strong things would follow for the Riemann-Zeta function. And in particular the Riemann hypothesis. So this was a little bit too good to be true. So people stopped believing Polya well before it was disproved. And when it was finally disproved by Brian Hazelgrove in when was this around 50. 1950, then I mean people were not as impressed as they probably would have been 20 years before that. So what Ingham did was that he said, there's this function am. You can define this for any positive number m. I'm going to think of m equals 1,000 in what follows. And then when you compute this function am, this is done down here. This is a complicated expression that has to do with the Riemann-Zeta function. These rho n's are actually the imaginary values of the roots of the zeros of the zeta function on the axis, the uh, axis that what with at a half. So essentially, you can do this for any m. You take all the roots of the zeta function between 0 and m on the imaginary axis, and then you plug this into the zeta function and has some e to the I value and sum everything up. Don't ask me how this works, but the point is that then the Lim sup of L of e to the x extended appropriately to the real axis times e to the minus x over 2 is bigger than or equal to this Lim sup. And the point is that this function am has a certain periodicity. It's what's called almost periodic. So this actually means that if you can find some x0 where am is positive, then that means that not only is there one place where L is positive, it's actually going to be positive on infinitely many values out to infinity. So all you have to do is to come up with a value of m and a corresponding value of x naught, so that when you plug this in, you get a positive number. And this is exactly what Hazel Grove did, and my program has terminated now. I don't think it did that much before we came back here, and you can see that I defined a in the appropriate way. This is surprisingly complicated. The point is actually that in order to do this, I need to know the zeros of, a list of zeros of the zeta function, and this is not built into Maple, but you can find it online. I found it on Odlyzko's homepage. He's a very prominent mathematician, so I assume he knows what he's doing. You can download this, and then I put it into Maple. I want to compute the sum of all the zeros up to m equals 1,000, so I need to know when I go above 1,000 for the first time. That's at entry number 650. So I add up these 649 terms, and then when you plug in x naught equals 831.847, then you get a non-negative, a positive element out, and this then disproves Polya's conjecture. So this was done by Hazel Grove, and it was done by him simply making this computation that we had to wait a few minutes for Maple to do. But as good as that might be, you also would like to know where the counterexample is. What is the counterexample? And if you inspect the inequality I just showed you, the counterexample that we found is going to be somewhere at e to the 831. So that's a huge, huge number. So there's no real good chance for us to checking this on the value. You can see I got to 10,000 relatively quickly, but in general, this is just too slow. So what you can do, and this was done by another mathematician called Sherman Lehman, is to say, well, actually, this function am turns out to be a good approximation of L. I don't think that's something that is understood exactly how good an approximation it is, but since we're just trying to be led by the A function to a candidate for finding a counterexample, the concrete counterexample to Polya's conjecture, what we can do is that we can simply look at A. This is what I've done this in Maple. It's the same thing that I just showed you, but doing these plots take a long time because you have to compute all these points and connect them with little lines. But if you look at the 1,000 from 0 to 35, you can see that it gets pretty big up at 34, but e to the 34 is a pretty big number. So after some trial and error, you get to think, okay, here, this doesn't look so small, right? So a number just after 20 doesn't look so small. And in fact, if you look at 20.6, what is it, 6,245, you get very close to 0. I mean, this is not 0. This remains negative, but this is a fairly big value of AM. And then you can go back to your experiment and say, well, e to that is somewhere in the range of 905 million. And 905 million is not completely out of the question. So you want, so this is what Sherman Lehman did, is he looked at these in this range and actually found a concrete counterexample which is precisely in that range. It's what is the exact number? 906,180,359. But the thing is that now the good thing is now I know sort of roughly where to look, but how will I find out if I have a counterexample here? And this is when you need to get a little bit clever about how you compute the L function. And I don't want to go into the details, but essentially the point here is that you don't have to compute all the intermediate values in order to compute L at 905 million. I mean, that's a very tempting assumption because of the way that the L function was defined. You take all these numbers and add them up. They're all plus and minus 1. So how can I save time? Well, it turns out that there's various tricks that you can do so that in order to look at 905 million, you don't have to look at all the intermediate values. You have to look roughly sort of halfway and then half again and so on. All of these methods were actually fairly well known at the time, even before computers, because that's exactly how this initial data supporting Polya's conjecture up to 20,000 was done by an Indian mathematician without using any other tools, paper and pencil, I assume. So you can do various tricks, and then it's very helpful to know where you're looking. So what happens here is that when you have a candidate for where to look at a counterexample, you can go in and compute there. And there's a program here that I did that uses various tricks with the Möbius function. I'm not going to go into that, but you can do this in a couple of hours. You can compute, for instance, what the value is of L at this number here that you're led to by looking at that graph. Then actually when you do this and you wait several hours, you will get minus 871, which is of course disappointing because it's a negative number. But then, I mean, it's negative, but it's not that negative. And then it actually turns out that if you keep on running a little bit after that, which is fairly easy because if you have a value, then you can get the next value by just taking the next number and factorizing that, and then you get the counterexample that I mentioned. So I think this is an example. It's one of the most sort of advanced example of how people are jumping back and forth between some very theoretical approaches and some computational approaches, and at the end of the day, they find out not only that Polya was wrong, but also they find the smallest example where he was wrong. This was not known at the time, by the way, because at the time it was impossible to do all the intermediate values, but this has been done now. So by doing efficient computations, it's actually known that this is the smallest counterexample.